Now that we have understood what are the various kinds of errors that can come up during a measurement, we can now appreciate that no matter how many times I do the measurement, I would never be able to correctly determine the exact value of the physical quantity. See, for example, if I take this remote and I am doing measurement on this remote, I am trying to measure its length, then the real value of this length is actually known as the true length. It is the true value of the physical quantity. All my measurements, I am trying to get as close as possible to the true length, but I will never be able to determine the true length of this remote. I will only be determined to some great approximation the length of this remote. If I repeat the measurements many times, then all of those measurements would come out to be different. They would be close to the true length if I am careful, but they would all be different because of the errors during the process of measurement. In other words, in all my different measurements, there would be some amount of uncertainty. And that uncertainty, when I'm doing the experiment, I really want to report that uncertainty so that other scientists can really appreciate, can understand what was the degree of accuracy with which I performed the experiment. So without uncertainty, if I report the results of an experiment, they do not mean anything. Okay, because the other scientists cannot really perform the experiment and understand to what degree of accuracy I actually perform the experiment. So with my experiments, I always want to report the uncertainty. So here is an example to demonstrate that. So here we have a crown, and this crown is, of course, the problem of Archimedes exists here. Now this crown, I want to determine whether it is made up of gold or it is made up of some kind of alloy. Now the people who are doing the experiment here are actually Tesla and Edison. So we didn't call Archimedes because he would have just determined it accurately, but we actually called the Tesla and Edison to do the experiments. And this is what they actually reported. So they took this crown with them and they were trying to find the density of the material with which this crown was made. So we were trying to determine the density. Now once we know the density of this crown, we can compare it with the density of gold or the density of the alloy and really understand whether the crown is made up of gold or it is made up of the alloy. So that's the ultimate purpose of the experiment. So Tesla took this crown to his home and he performed some experiments, and then he said that, oh, according to my experiments, this is the range of possible values for the density of this crown. So he said that it could be between 13.5 to 16.5. Edison also took this crown and he came up with this result that, okay, so the range of density for this crown could be between 13.7 to 14.1. So if we plot these ranges, notice that the Tesla's range is centered around 15 and it can go to plus 1.5 and minus 1.5 in either direction from 15. And we represent this fact using these symbols. So what we say is that Tesla's measurement, we will report it as plus minus 1.5 and we'll take the unit common, gram per centimeter cube. And what this really means, that Tesla is not really sure. He's not really sure that his measurement is exactly 15. He is saying that his measurement lies in a range around 15. It can go below to 15 minus 1.5 or it can go above to 15 plus 1.5. And that is the fact we have represented here. So this is Tesla's measurement. Now we come to the Edison's measurement. So what is Edison saying? Edison also performed the experiment, and of course his range of possible values for the density of the crown comes out to be much tighter. He says that it is around 13.9. okay, so that is the 13.9. It is around 13.9 and it can go plus or minus 0.2. So it can be either plus 0.2 or it can be either minus 0.2. So it can be in a range of 13.7 to 14.1, and that is the fact that we have expressed there. And we represent it when we report the result using this. So it is the best estimate, which is 13.9 plus minus the uncertainty or the error in the measurement 0.2. So again, this represents a range of possible values for the density of the crown. Now you would understand by looking at this figure that Tesla's measurement is not actually very useful, unfortunately, because In his range of measurements, it covers both the density of gold as well as the density of alloy. So based on Tesla's measurement, we really cannot conclude whether the crown is made up of gold or it is made up of alloy. On the other hand, Edison's measurement is good for our purposes because using this range of measurement, we can safely conclude that the crown is only made up of alloy. So think about it. Okay, so one thing to note here is that even though Edison's measurement is also not very accurate, it is not that it is accurate to 100th decimal place or 1000th decimal place. It is accurate enough for our purposes. That is the main thing to note here. We only do the experiment to the accuracy with which it is sufficient for us to make a conclusion. We don't have to go to infinite precision accuracy. So that is the first thing to note here. And the second thing to note here is that our result we would always express in the form of best estimate, that is what we think the true value of the quantity is, and around that we will put some range for which we are really not sure that okay, so our best estimate can vary by this much, either it can go above by this much quantity or below by the same quantity, and this is how we represent our final results of an experiment. So now let's understand how they could have possibly arrived at these values. How Tesla could have arrived at these values. So he would have done the experiment number of times. Tesla would have done, for example, his experiment 4 times. And then he would have said that, oh, let me just take these average of those 4 readings of the density that I have taken. And the average of these values comes out to be 15. Then he would have said that, oh, let me assume that my average is the real value of the crown's density and find out the error in each of these measurements. So error in each of these measurements is actually equal to the average value minus the measured value, or we'll just say measurement. Okay. So if I subtract each of these measurements, I am subtracting each of the measurements from the average value of 15, I would get the uncertainty. Okay, so 15 minus 13 would be 2, 15 minus 16 would be minus 1, and similarly we'll get 1 and minus 2 also. Now I want to find the average uncertainty. What is the average uncertainty or the average error across my measurements? So you would just say that, oh, let's just take the average of these 4 quantities, these 4 uncertainties. Of course, if I take average of these 4 uncertainties, it would come out to be 0, which is not what we want, right? Because my uncertainty is not really 0. I know that there is some uncertainty, there is some error in my result. It is not really 0. So I cannot just say that my uncertainty is 0. So to avoid that problem, what I do is that instead of finding the average of these quantities, I find the average of the absolute values, okay? Absolute values of these quantities. So absolute value actually means that I discard the sign here. I only take the quantity. I only take the magnitude of each of these numbers, and I take their average. So minus 1 actually becomes just 1, and again our minus 2 here just becomes 2. And of course we are taking the average, so we have to divide by 4, and this comes out to be 1.5. So this is how he came up with this average uncertainty of 1.5, and then he used the average value, which according to him is the best measure of the true value, and then he said that the range of uncertainty around this true value is 1.5. One thing that I want to really point out here is that we are using the average value to determine the errors. The ideal thing would be to actually use the true value. If I knew the real length, if I knew the real density, my error in measurement would be my real value minus the measurement. You would agree, right? That is the real error that I am committing during the measurement. But of course, since we don't know this, we just don't have the value, the true value we don't know. So we say that our average value is our best approximate, is our best guess of the true value, and we use it to compute the errors in the measurement or the uncertainties in each of the measurement. So similarly, the Edison would have done the same process. he would have first computed the average, which would come out to be 13.9. Then he would have computed the uncertainties, for which he would have subtracted from this average each of these values. And when he did the subtraction, this is the results that he would have gotten. Of course, as we did in the last time, to calculate the average of these errors, I would not use their, I would use only their absolute values. I would discard their sign and I would only use their absolute values. And this is how my average would come out to be. Very, very simple. Okay, nothing difficult here. Divided by, this will be total 5. So he took the 5 readings and this comes out to be 0.2. And finally, he would have represented his results as 13.9 plus minus 0.2. And notice that we put the unit outside. Okay, so we write both our measurement and the uncertainty, and then we write a unit common to both. So the unit applies both to this measurement and to the error in the measurement. Now that we have understood this, let us now understand what do we mean by relative error. So one way to report our result in this case was, we would just write it like this. And we will say this is, of course, gram per centimeter cube. Another way to report the same result is to take out 15 common. Okay, so we will just take out 15 outside and we will write the result as 1 plus minus 1.5 divided by 15, and this remains in gram per centimeter cube, because grams per centimeter cube, the unit does not really change. This quantity right here is known as the fractional or relative error. So this error is not absolute, it is relative in terms of the measurement. So our measurement was 15, the error was 1.5. We divide the error by measurement and we come to relative error. Relative in terms of what? So this error of 0.1 is relative to my measurement, so which was 15. And of course, because I am dividing 1.5, which is given in grams per centimeter cube, so this 1.5 is given in gram per centimeter cube, and this 15 is also given in gram per centimeter cube. This quantity right here becomes dimensionless, and this is how I would report my result using relative error. Okay, and this 0.1 is relative to our measurement. It is no longer absolute. Now if we want to convert into percentage, we just multiply this by 100. Okay, so this 0.1 into 100 and this comes out to be 10%, and we say that my error is 10%. Okay, again 10% of what? 10% of my measurement, so which was 15. Similarly, in the case of Edison, we can do the same process. His relative error comes out to be 0.01. So using relative error, if he wants to report his results, he would do it like this. So he will say 2.9 and then 1 plus minus 0.01 gram per centimeter cube. And of course, then again we can, even in the case of Edison, we can compute the percentage error, and that would come out to be around 7.1. Okay, so this is this is incorrect. Okay, so this is actually incorrect. If you compute the percentage error, this comes out to be around 1%. Okay, which is true, because in the case of Edison, we understand that the error was much less, and that's why we were able to make some kind of conclusion. Okay, so this 1% comes because we multiply the relative of fractional error by 100, and this gives us a result of 1%. Okay, so I could report relative error either as fraction, in which case it is known as fractional error, or I could report it as percent, in which case it is known as the percent error. Okay, so the answer for Edison would be 1%. So now with that we come to the next important topic, which is how do we actually state the uncertainties. So now we have understood how do we compute the uncertainties, absolute uncertain errors, how do we compute the absolute error, how do we compute the relative error and the percent error. We have understood all of those things. How do we now report that uncertainty? So here is an example. So I have the measurement of the G, which is the acceleration due to gravity. I have measured it using some means, and I have done several measurements, and across those measurements my error comes out to be Okay, so this is the error. Okay, it comes out to be 0.02385. See, one of the things that you would understand is that I know that I have the error in the 100th decimal place. I already know that. I'm not really sure about even the 100th decimal place. So there is no point in reporting more accuracy after that. So there is no point in reporting that, oh, I have more accuracy in the 1000th place, in the 10,000th place. So there is no point, okay? So the first rule is basically that whenever we report uncertainty or whenever we report the error, we always report it only to one significant figure. What is significant figure? To find out the significant figure, we just ignore the decimal point for a second. We start from left, okay, and we look at the first non-zero digit. So first non-zero digit is actually 2, so that would become my first significant figure. So in this case, my first significant figure is 2, and I only report my error to one significant figure. So I discard all of these. These are useless, okay, because I am not even sure about the 10th place, 100th place, sorry. So there is no point in reporting more significant figures, more digits after the 100th place. So I only report my error to one significant figure. Now the second rule, okay, so in this case, my acceleration due to gravity, I would report it as 9.82 plus minus 0.02 meter per second square, okay. Now the second rule basically is that we do not, based on the error that I have come up with. So for example, here I have come up with the error of 0.02. I now modify my measurement, right? So even in the case of the measurement 9.82, I would modify based on the error. So how would I do that? Let's just see here only. So for example, let's say that I did the average and the average value came out to be this much. This is the average value that came out to be. It just came out to be 9.823. Now, based on the uncertainty, I know that there is uncertainty in my 100th place. What is the 100th place here? It is 2. So, I am not even certain about the 2 there. This 2, I am not really certain about. So, there is no point in giving more figures after 2. If I report this 2, 3, 6, 7, that all of those are useless because I am not even sure about this 2. So how can I be sure about this 3? I cannot be sure. It could be 3, 4, who knows what it is. Okay. So based on the significant figures in my error, I now change my quantity, my measured quantity, the measured value, to have the same order of magnitude as the order of magnitude of my significant figure in the error. So here the significant figure in the error was 100th decimal place. So I would not go beyond the 100th decimal place in the case of my measurement also. So this 9.82, I remove 3 and I only report till the 100th decimal place. So that is the second law. In my answer, I only report my answer to the same significant figure as in the case of my error. So that is the, let's take another example and understand that. So let's say that my measurement of some velocity of some airplane, some rocket, it came out to be this. Last significant figure here is actually 1. The last significant figure in the stated answer, which means that here the last significant figure is 1. However, here from the error, I know that I am even unsure of the tens place, right? So this is units place, this is tens place. So I know that I have error after my tens place. So here I cannot really report the units place. How can I be sure of the units place if I am not even sure about the tens place? I know that there is error in the tens place from the error. So my last significant figure, okay. So this is the first significant figure in my final answer, and this is the last significant figure. So this is last and this is first. I am talking about the last significant figure in my answer. The last significant figure in my answer should only be the same order of magnitude as the error. So since my error is in tens, so I cannot have the last significant figure in ones. So I would just change my last significant figure to be, I'll just round it up. I will just round it, basically round it down to the tens place. And my answer would come out to be 6050 plus minus 30 meter per second. Okay, very, very simple. Okay, so this is how I report the result. Because my error is till the tens place, is in the tens place, therefore I round my final answer also to the tens place. As simple as that. Let's take another example and now understand it a little bit better. So here I have 9.82 plus minus 0.03. Okay, so this is my final result. This is how it has been reported. And this, I don't really have to do anything because the significant figure is in the 100th place. So I can keep the 100th place here and I'm fine. What happens if my result was, my error was not in 100th place, but it was in 10th place. It was one place after decimal. In the 10th place, there was an error. My error was 0.3 instead of 0.03. Then I know that there is really no point in reporting my result because I am not even sure about this place. So there is no point in reporting the result after that. So I will round my result only till the 10th place. So I will just say it is 9.8 plus minus 3. Now what if my error was in the units place? So now my error is plus minus 3. So in that case, there is no point in this anything after the decimal point is useless because I am not even sure about the 9. I'm not even sure about the 9. So what I'll do is that I'll round it up to the units place. So this becomes 10 plus minus 3. Okay. So there are two rules. First rule is that we only keep one significant figure. We start from left and only keep one non-zero digit in the error. Okay, so my error should only be one significant figure. The second rule is that in the case of my final answer, I round it to the same decimal place as the significant figure I have in the error. So if my error was in the units place, as in this case, then I would round my final answer to the units place. It was in one place after the decimal point, then I would round my answer to that. If it was to the 100th place, if my error was, the significant figure in the error was to 100th place, I would round my answer to the 100th place. And those are the two rules that we would use to report the final answers. And as long as you are doing that, you will be fine. You will get 100% of the mark in the numerical. Now, let us try to derive the formula for the absolute error in general terms. So we have just seen an example. We have understood everything using example. Now we will just derive the same formula in general terms. General term, what does it mean? It means that let's say that my measurements, instead of being numerical quantities, they were just these algebraic quantities. So my measurements were A1, A2, A3 till AN. So those are the measurements that I have taken. Okay, so in the case of Tesla and in the case of Edison, we have already seen that. So the average value of the observations, we already know it would be A1 plus A2 plus ... AN divided by N. So that is simple average formula for average. Nothing very special here. This is just simple formula for the average. And we write it concisely. Okay, instead of writing it like this, we just write it concisely in this form. So what this means is that I have the subscript here I, which goes from 1 to N. So it goes from 1 to N. Okay, and this is the summation sign. It says that all of these AI values I would add. Okay, so here I would write it as AI. I goes from 1 to N. So I would expand. If I have to expand this particular thing, okay, it would be expanded to this quantity. Okay, what all it is saying is that my I value takes a value from 1 till N. So it becomes A1, A2, A3, A4, A5 up to AN, and I sum this because this is a summation here. I sum all of those quantities. So that is what I have written here in much simplified terms, and of course I divide this entire thing by N, and that is what we have written here. So that is the average value of observations. Now there has been error in each of those observations. We know that the real value of the error is actually equal to true value minus the measured value. So it would be A true minus A1 for the first one, and we denote it by delta A. Okay. But of course, we really cannot find the true value. The true value A true we don't really have. I mean, there is no value given for us. Okay, we are just trying to do the measurement and find it out ourselves. So this A true is not really known. So we don't use A true here, but instead we use the mean that we have calculated earlier, and we just assume that this mean is the real value. Okay, so this mean, A mean, is the true value. That's what we have assumed. So now we compute this delta A's, which is essentially the error in each of these measurements. So delta A1 is equal to A mean minus A1. Delta A2 is equal to A mean minus A2. So on and so forth. We can compute till AN. Okay, delta AN is equal to A mean minus AN. Okay, very simple. So here we have computed the error in each of those measurements by using the mean as our basis. Now what we do is that we sum those values. We take the sum of these values. Of course, when finding the sum, there would be some positive quantities here, some negative quantities here. So we cannot take the sum directly. So first we take the absolute value of this measurement, of this error in our measurement. We take the absolute value and we sum those. So that's what we have done here. And this is the mean of the errors. So this is the delta A mean, or mean of the errors. And that is simply we take the absolute value of each of these errors and we find their mean, find their mean or arithmetic average. Now our final reported result becomes A mean, which we have computed here. So this was our A mean. Okay, this is our A mean, plus minus, of course, the error. Okay, so we can go in either direction. Either we can we have a range of instead of just having one measurement A mean, we have a range of measurement, and that this range is given by what? This range is determined by how much errors we had in the our measurement. So this the mean of the errors we use to actually generate the range. So delta A mean we use here. And what would be the relative percent error? The relative percent error we denoted using small delta. Okay, so this is large delta and this is small delta, Greek letters. Okay, this is known as delta, this is Greek letter, and this is small delta is also Greek letter, but this is small. Okay, similar to how we have the small, the capital and the small letters in English. So this becomes delta A. Of course, if we want to calculate the percent error, we take the delta I mean, the mean of the errors divided by the mean of the quantity, and we multiply it by 100. And we have understood all of these using the example earlier, and this is just writing those things in general terms so that we can come up with formulas. You don't really need to remember these formulas. It is very simple to understand it. Now here we solve an example. So this is a simple pendulum, and I have a stop clock using which I am measuring the time period of this pendulum across various oscillations. Of course, as we know that the time period of pendulum does not really change. So if I am doing these measurements, if I have gotten these readings for the time period of the pendulum, obviously they are all incorrect, because time period should not really change, but that is to be expected, right? I always have some kind of error in my measurement. So now we want to find out what is the error in our measurement, and how do we measurement of the time period, and how do we finally report it. So what we'll do is we'll first know the measurements. We know that we compute the mean. So A mean would be the mean of all of these values. So it will be 2.63 plus 2.56 plus 2.42 plus 2.71 plus 2.80, and we take the mean of all of these quantities, and of course there are 5 measurements. So this mean comes out to be 2.62 seconds. Okay, so this is the A mean. Now what about error? So we can compute the error also. So delta A's. Okay, so our errors, how do we compute it? We use this mean 2.62 and we subtract each of these quantities in turn. So the first one comes out to be 0.01. I subtract From 2.62, I subtract 2.63. Okay, so 2.63 is larger. So 2.62 minus 2.63, and then I'll do minus 2.56. And this will give me the various errors. Okay, and this will come out to be, the first one will come out to be negative, the second one will come out to be positive because this is smaller, the third one will come out to be 0.2, again positive because this is smaller. Since this is larger, the next one would come out to be negative, and this is 0.09, of course minus 0.09, and then finally we will have we will have again a negative value of 0.18. Okay, so these are my delta A's, or my various errors in the measurement. Now I calculate the delta A mean. I compute the mean of these errors, and what do? I first take their absolute values. So I discard the sign completely and I just simply find the mean of these errors. And of course, we will divide it by 5. If you calculate this, this comes out to be 0.11. Now, as we have seen, we will only keep one significant digit in our error. So we discard this. So we start from left. The first non-zero number we encounter is 1. We keep that and we discard this completely. So this one is gone and my error comes out to be 0.1. And this error has the same unit as my measurement, which is second. So how do I report the final result? I will report it as 2.62 plus minus 0.1 second. Now, of course, because the significant digit in my error is the 10th digit, so there is no point in giving more accuracy to my measurement. This 2 is kind of redundant because I'm not even sure about this digit. So I will round this number to the 10th place and my final answer would come out to be this. Okay, so that is my absolute error, the quantity measurement expressed as absolute error. Again, the same thing we can express as relative error also. How do I do that? I know my relative error would be 0.1 divided by 2.6. If I want to find out the percentage, I would multiply it by 100. Okay, and this you can do it yourself. Okay, so this is very, very simple. We can find the absolute error, we can find the relative error, and we can find the percentage error as well. Now here we come to the last section in which we will be finding, we have already found, we have done some experiments and found these values, and now we want to express them in the appropriate form. And this is very important that you understand this, because in the exam you will be asked to represent the quantities in the correct format. Okay, so the very first one is very, very simple. Okay, so the error, we always keep only one significant figure. So we start from left and we first only keep the first non-zero digit in the error. So we remove this 0.12 and we keep only till 0.03. Of course, because we know that we have errors in our 100th decimal place, so we have error in this decimal place, there is no point in reporting the result beyond this 100th decimal place. So I discard the rest of the digits even in the case of my measurement. So this final answer comes out to be 8.12 plus minus 0.03 meter per second. The next quantity x is given in the terms of 10 raised to power 4. So it is given in terms of, it is a length which is given in scientific notation. It is given as 10 into 10 raised to power 4. There is some exponent here, and that is the trick here. So what we'll do is that the way to do it is we use the same power, okay, exponent even in the case of error. So we convert our error to the same exponent and we take the exponent out common from both the result as well as the error. So this becomes 3.1234 plus minus 0.0002 into 10 raised to power 4 meters. Of course, our error, the significant digit in our error is, this is 10,000th digit. So we are allowed to keep this 4, which is also there in the 10,000th place. So we are allowed to keep it. And the only thing that we needed to do is that we needed to remove bring out the exponent out common from both the measured quantity as well as the error. And that is the way to report the result if we have 10 raised to power. If the results are given in scientific notation, then we always report it in this format. We take the power of 10 raised to power outside, common to both the value, the measured quantity as well as the error. Next one is also similar example. Here also we will do the same thing. So we will take out this 10 raised to power minus 7 out. We will just take it out common. So this will become 5.6789. Okay. And of course, we will say plus minus. This will become 0.03. Okay, there is no additional 0, and this will be into 10 raised to power minus 7 kg. Okay, so I divided this by essentially by 100. Okay, that is what I have done, and I have taken 10 raised to power minus 7 out. Very, very simple. Okay, now the problem here is, of course, that this is our error. The significant figure in our error is to the 100th place. So we will only round the result to the 100th place, even in the case of our measurement. These two quantities do not really have any meaning. There is no meaning. There is nothing there. Nothing here. We cannot be certain about this. There is no point in reporting this. So we round it up to the 100th place, and this comes out to be 0.3 into 10 raised to power minus 7 kg. Okay, so this is the correct way to represent any of these quantities. This is the right way to represent any of these quantities. Hopefully things are very clear now. In the next class we will discuss about the propagation of errors. So how do, in the formulas, when we have errors, then how do we propagate the error in the on the left hand side, right? So for example, if I have force is equal to mass into acceleration, I have measured the mass, I have measured the acceleration, I have errors in all of those, both of those, mass as well as acceleration. So how do I propagate those errors in the mass and acceleration to the force? And that would be the topic of our next class. Thank you.